Hi everyone, I'm Fausto Bisanti, a PhD student at the University of New Hampshire, and today I would like to talk to you about the project that UNH is collaborating on with VTrans. And the name of the project is Recycle Asphalt Shingle as a Full Depth Reclamation Mechanical Stabilizer. So with this first slide, I would like to show you how the project was born. So based on data from the state of Vermont, it has been found that approximately 25,000 tons of waste shingles are produced annually in Vermont. And Vermont state law requires recycling of shingles. So the use of RAS, recycled asphalt shingles, in road construction is already well known. For example, for hot mix asphalt processes, or for as an aggregate in rural road, or for structural fill. So our question was, is it possible to reuse RAS in FDR processes, so full depth reclamation processes, so as a mechanical stabilizer in the deeper layers of the pavement? And our research approach starts with a comprehensive review of the state of the art and practice of the FDR processes and the use of RAS in asphalt pavement. Then we developed the experimental design with sample material from two different VTrans projects and RAS from two different sources. And laboratory characterization involved physical, environmental, and mechanical tests. Then we analyze the data, and our goal is to develop recommendations to VTrans about the reuse of asphalt shingle in FDR processes. For the experimental design, we start evaluating the baseline FDR materials, so as constructed materials. Then we evaluate also the blends, FDR materials plus 5 or 10% of processed RAS, so passing 3/8 inch from two different sources, manufacturing waste and post-consumer RAS. As a result of this analysis, 5% was identified as the optimal dosage. Then we decided to implement the analysis using 5% processed post-consumer RAS at increased density and using the same adjustment to evaluate also 5% unprocessed post-consumer RAS. And the objective of the increasing of the density was to achieve bulk densities and air void contents comparable to those of the corresponding FDR baseline. In this slide, you can see the main results in terms of indirect tensile strength. And the two graphs show the results of the test performed on samples fabricated with the two baseline, so MD and CNJ are the two baseline. The baseline plus 5% of processed post-consumer RAS, and the baseline plus 5% of unprocessed post-consumer RAS. Also in the plots, the tensile strength ratio is shown, that is an index of moisture resistance, and also the air void contents are shown in the parentheses here. And also the VOT threshold of 40 psi. That is the threshold for the ITS from the new VOT specification. And we can see that using unprocessed 5% unprocessed post-consumer RAS lead to an increase of ITS of up to 40% compared to processed 5 post-consumer RAS for Marshfield-Danville project. And also incorporating RAS leads to an increase of moisture resistance, either processed post-consumer or unprocessed post-consumer. For Cambridge Johnson, the use of 5% processed or unprocessed post-consumer RAS does not cause a statistically significant change in ITS compared to the baseline. And the threshold of 40 psi imposed by the VAOT new specification is always respected, and the moisture resistance also in this case increases with shingles. So as a General results, we can say that use of shingle increased the moisture resistance, and a dosage of 5% unprocessed post-consumer asphalt shingles can be considered an appropriate and sustainable option as a mechanical stabilizer in FDR processes. Thank you for the attention.